Quantum gravity research often reminds me of the 1963 classic comedy, It's a Mad, 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 Mad World. In the movie, a criminal crashes his car and, with his dying breath, reveals to the occupants of 4 passing cars that he has buried a large sum of money under a big W in a state park. The humor comes from the insanity and mishaps that the 4 treasure-seeking groups experience on their way. In a way, you can see the same kind of humor in quantum gravity research. The pioneers who bequeathed us quantum theory and gave us the most successful physical theory of all time, with their dying breath, essentially told us that we had to solve this last elusive problem. Since then, it's been a mad dash to try to come up with the answer. But here's the twist. Our predicament is considerably worse than those comedic fortune hunters. While there may be a big W in a state park somewhere, we have absolutely no way of reaching it, and the ground is frozen solid. Unlike other problems in physics, where there's an appreciable amount of data to distinguish true from false hypotheses, quantum gravity offers none. There are very few experiments we can do to rule out hypotheses and none to rule out the major contenders. String theory has always been the favorite to win this contest. It has had the smartest people, the most funding, and the most elegant solution. The theory could be confirmed if there were any data. There isn't anything specifically wrong with it. It's not like we are going to find a math error in the theory one day and conclude that it was never a good idea in the first place. String theory proposes that all matter is made out of strings vibrating in higher dimensional spaces. All the ways the strings can vibrate in those spaces tell us what kinds of particles can exist. Imagine a grand symphony, where each instrument represents a different vibrating string. The melodies they create shape the universe as we know it. String theory goes with supersymmetry like pancakes and maple syrup. Supersymmetry tells us that for every kind of particle we know, such as electrons, quarks, and photons, there is a heavier companion particle. If the known particle is a fermion, meaning it has a spin that is a multiple of 1/2, then its heavier partner is a boson, with an integer spin. If the known particle is a boson, then its heavier partner is a fermion. However, not a single supersymmetric partner particle has been discovered so far. Either they are too heavy for current colliders, or they don't exist. Loop quantum gravity is the next most popular theory in the realm of fundamental physics. It's less pretentious than string theory, not aiming to be a theory of everything. Yet, like string theory, without data, there is no hope of confirmation. LQG takes a formulation of general relativity and breaks it into what are called spin networks. These networks are the underlying form of space in a discrete form. Imagine a lattice where each node and connection represents the fabric of space itself, dancing in a quantum ballet. These spin networks weave the very tapestry of reality, threading through the cosmos in a mesmerizing, intricate pattern. There are many other theories. In fact, everyone seems to have their own pet theory. Many physicists and non-physicists alike, including the retired engineers of the world, hope that their theory will one day be recognized as the correct one. They envision a time when, like Einstein's general relativity was confirmed during the 1919 solar eclipse, their name will be broadcast throughout the world. Yet history tells us that such moments are rare. Einstein was unique and lived in a unique time. To be honest, physicists' names are broadcast throughout the world all the time these days, but they don't seem to become famous like Einstein for it. The most famous physicists today are known for best-selling books and hit TV shows, not just theories. Even within fundamental particle physics, fame often comes not for actual discoveries, but for theories or mathematical proofs so elegant and groundbreaking that they captivate the scientific community. There is a lot more to be gained from trying to explain dark matter or dark energy, or at least some currently unexplained phenomenon, than quantum gravity. And there is even something to be gained by spending your life working on a millennium problem. Even if you fail, as you probably will, at least if you succeed, people can tell you did. Any theory that can propose a new test that can be done with current technology is already miles ahead of the competition. Almost none can. This was why Einstein's theory mattered, not because it was a cool new theory, but because he proposed several tests, a couple of which could be done with the technology of the early 20th century. People didn't like his theory at the time, but they were forced to accept it on evidence. Many people these days, including physicists, have decided that gravity isn't quantum. That means that gravity somehow interacts with quantum matter, but is itself not quantized. A recent paper came out proposing a workable theory for how this might be possible. It calls the idea a post-quantum theory of gravity. Post-quantum is kind of postmodernist. It suggests that we are entering a new philosophical era where we turn against the old quantum ways, not to return to our classical roots, but rather to question everything we thought we knew. Gravity may not be quantum. Quantum theory may not be fundamental. This solves a pernicious problem in quantum theory called the problem of time. Quantum theory likes to have a wave function that evolves in time, but what is time in general relativity? Time at different points in space run at different rates. Time is multi-fingered, to use a technical term. The post-quantum theory suggests that space-time has random fluctuations in it that can be measured. If you put an atom in superposition, meaning it is effectively like being in two locations at the same time, then it must have two separate gravity wells. The theory suggests that random fluctuations will break this superposition after a certain amount of time.